foundation for all the experiments or all the uh, experiments that you will do in your future. This is a very fundamental to that, and hope uh, that we have a discussion on the same. And okay, let's start. So in this tutorial, we will be using Torch, PyTorch specifically, for all our neural network based assignments. So we load all the libraries. We have Torch library. The NN is the neural network module. Transformer, I don't think we will be. There are transforms. It just transforms the data set which we will see, and we have the data set. We will use the data set that is already there. In our case, we'll be using MNIST data set. It's an. We'll see what it is. We have some math function and a plotting function for plotting our graphs. Okay, so let's load all our libraries first. It's take time a bit. Just a sec. Okay, so we are done loading. Now we will load the MNIST data set. You can see. So we want to train this data set and we want to transform into a tensor form. So when you download the data set, which is download true, it will download it in a numpy value. As you have seen before, the numpy is numpy array. So you want to transform into a tensor, so which is like the torch way of handling numbers or matrices. So you need to convert into tensor. You have said train, that you want to train with this data set as train true, and where it will be downloaded is it will be downloaded at dot data file. So you will see that there will be a data file, dot data file will be created here. So let's download all the data set now. So currently it's downloading, and yeah, it's downloaded, and you can see the data directory has been created, and you have MNS data here with some raw images should be there. There you go. So you have a file which is in ubyte type, and you can see that this is test file and then this is train images. Okay, so you have your test and train image downloaded here. Okay, so now once you have downloaded your test dataset and a train dataset, so you can easily see now. Now let's convert into, let's look into what this dataset looks like. As we have discussed before, batch represents the size of the data that you want, like how much chunk of data that you will draw from the dataset. So we will do 3000 iterations. We will run this algorithm for 3000 times step, and the number of epochs is similarly that how many iterations you want and what is the data size. Okay, so let's now load the data set in the data loader using the torch function. So this train loader just simply loads all the data set that you have already downloaded into a in its RAM memory. That this function will contains all the images. So you can see that we have loaded both the data using this function, the train loader and the test loader. And now we will just try to see what this images contain. So we will see we will have images label. Train loader has image and label information, the X and the corresponding Y, the image and the corresponding label Y, and we will plot all these things. So let's look into what does it plot. So MNS data is a number data. So you see that this is a handwritten data, which is number 5. Since it has been expanded to such big, that's why you see that the pixels have started to break. But it is not such a big data. It's a very small handwritten digit number. But it's just that the image has expanded, so this looks like it's a broken. But it's a handwritten digit 5, and the label corresponding to is 5. It's a hand digit written 2, the number is 2. It's 1, 1. So the goal is to train a neural network such that given an image of a number, you need to identify that number. Okay, so this is the goal. So we have the image and the corresponding label 9. So we have this kind of data set, a handwritten digit 5 and 5, handwritten digit 6, 6. Okay, handwritten digit 8, 2. So you can see this 2 and this 2 is very different. But the machine, your neural network algorithm needs to learn a function such that it can able to identify or classify this image as 2. This is the goal. Okay. I will wait for a while to see if the data set is clear that given this image and your goal is to identify this number as 5. So image and the corresponding label 5. So this is the training set, and now you need to train them. So we first loaded all the data set, training data set and the testing data set, and we saw some of those images, how those images looks like. And now let's go further now. Okay, let me just wait for a while to see if everyone is able to follow till this part. You can see 0 looks like 0. This is 8. This is 4. So this is also 0. This is 6, 9, 6, 1, 5, 7, 2, and 4. So the machine learning algorithm needs to identify all these things. Okay, so let's go further. So now let's convert everything. So let's make sure that we are doing it properly. So we have the batch size at 100, number of iterations is 3000, and you can see the number of epochs is simply how many iterations you want and what is the data size, total data size. And that's you have the number of epochs is just simply integer value of this value, and you loaded all your train data set and the test data set. Okay, so let's load all the training data set and the test data set. Now here is the neural network model that we have learned yesterday. Okay, so let me just on a side, let me just open that. Okay, I don't think it's give me 1 second. Let me just open the new slides once. Oh yeah. So now we have seen that this is the input layer, hidden layer, and the output layer. So let's construct this similarly. So you have input dimension. What is the size of the input? Hidden dimension. Input dimension in this image that we have 3 input dimensions. So the input dimension is 3 because there are only 3 features here. That's what input dimension is. Hidden dimension. How many hidden? What is the hidden dimension there? 1, 2, 3, 4. This is the 4 dimension hidden dimension, and the output dimension is 2. So here input dimension, hidden dimension, and output dimension. That's what it is. So now let's create this model. So you initialize your. So you need to first create a class, and that should be a class. That should be a subclass of nn.module. This is the neural network module. You initialize with a linear layer, which is nn.linear, input dimension and hidden dimension. So it will create this weight matrix. You remember that we have to create a weight matrix here. Where did that go? This one. No, not this one. Yeah, this one. So nn.linear will create this weight matrix. Okay, so this W matrix will be created with FC1, which takes the input dimension. So which is the input dimension is 3, and the output dimension is here is 4. Right. So this is what it has created. So it takes input dimension and an output dimension, which is the hidden dimension here. Then you add a sigmoid activation function. You want to add a sigmoid activation function, and then another hidden layer is there. So you have this another V matrix is there, right? So you need this V matrix. There you go. So this is your another V matrix, hidden dimension and output dimension, and that completes your entire model. Right? You have your activation function, sigmoid, and this is your linear layer. So what you have to do is that you need to tell them what is the forward pass. How will the forward pass looks like? So you take given an input x, you pass it with the first layer. So which you do W transpose X transpose W, right? So you just simply do FC1 of X, which is FC1 is the linear layer. You calculate, you get the output. You apply a nonlinear function, and then again send it to the next output, which is this V function. You send it, and then this is the output, and return that output. That's it. So this is your entire neural network module. Okay, so let's run this neural network module. Now in our case, the input dimension is an image of 28 cross 28 dimension, which is 784 is the total number of input dimension. 28 cross 28 is the image, so the total is, remember you just multiply 28 square is 784. So the input dimension in this our example was 3, but in our MNIST data set, the input dimension is 784. So it's a very long vector. So single image of say 9 is a 784 dimension. It's a 28 cross 28 image. So you can see there is 0 to 28 here, 0 to 28 here. So this is a 28 cross 28 image, and there are 784 such pixel points. So 784 points, that's the input to this neural network, 784. And the output is, you need to identify either it is 0, 1, 2, 3, 4, 5, what number it is. So 0 to 9. So the output dimension is 10. Here it was 10, here it was 2, the output dimension is 10, because you need to identify whether what number is it. Is it 0, 1, 2, 3, whether it is 9. So this is the goal. So the input is 784 or 28 cross 28 image, and the output is a 10 dimension vector. So even though the output is a 10 dimension vector, as you have seen before, that in the example that we saw here, a car prediction, car or bike prediction, that one of the neuron will predict whether it is a car, whether it is a bike, right? And whichever has the highest probability, you choose that it is a car or a bike. So in this toy example that we see here, you send the image of a car and say it predicted a bike with the probability of 0.81 and it predicts car with probability of 0.151, right? That's how there were two kinds of predictions that you needed to make, either bike or car. Here we have 10 such predictions to make. Either it can be 0, 1, 2, 3, or something in between to till 9. We also have said that our hidden dimension that we want to set, we have set it to 100. You can set it to any number and you can play with this tutorial, but for this sake of our tutorial, we will choose a hidden dimension of 100. You can choose any other numbers and you can play with it, but how does the behavior change when you actually set a hidden dimension to say 1, as extreme as 1, or a very large number, say 1000. So you can play with those numbers, but for this part of our tutorial, we'll just focus on a hidden dimension of say 100. So now your input dimension is 28 cross 28, hidden dimension is 100, and output dimension is 10. Okay, and now you will create this model, your neural network model, using this information: hidden input dimension, hidden dimension, and output dimension. Let's create this. So now you have created your neural network model. Now once you have created your neural network model, the way to learn is now to define your loss function. What loss function are you going to optimize for? But before we move into any further, let's just wait for a while to see if there are any doubts in creating the model itself. If anyone has any doubt till this point of creating the model. Okay, seems like there is no doubt. Okay, so okay, so let's continue if there are no doubts then. So let's define our loss function. The loss function is simply a cross. We are in this case we are using a cross entropy loss function. Cross entropy loss function simply measures. So when you are using a classification task, it's much better to use a cross entropy loss function, because the loss function gives you a better idea of how far or close your predictions are. So what it does is that, say for example, your prediction. So this is how it is defined. Say your prediction is 1. So the true value probability is 1. So your prediction value is say something thing between 0 to 1, so 0.89 something. So this is what it will predict. So log of 0.89. But if your prediction is 0, so this term will become 0 and 1 minus log will be there and 1 minus prediction will be used there. The cross entropy loss functions measures the distance between the two probability distribution. So in our example that we discussed last time, we were using mean squared error, which actually was good for doing regression. When you want to do regression, it is good for doing that. But when you want to do a classification task, we generally prefer to use cross entropy loss function. It's not that we never use mean squared error in classification task, but it is mostly preferred if you use a cross entropy loss function because it can handle, it measures the distance between the two distribution or two classification tasks really well. So we use the cross entropy loss function. So now once we have defined our loss function, we'll define the learning rate. Remember that for each of this thing, we need to calculate the gradient and eta, which is referred as learning rate. Eta is referred as learning rate in our in general in neural network. So this is how it looks like, right? So you need to calculate the gradient with respect to the parameter that you want to take. Now, you need to move in the negative direction, and eta is the learning rate. So it's very simple. So learning rate you have set to 0.1, and this gradient calculation that you want to do is simply done by SGD. So when you call SGD, it is called stochastic gradient descent. And you have model dot parameters, which actually just simply takes prints out takes all the parameters of this model. In our case, it is only W and V, right? So it was a two-layer one hidden layer neural network, which will have W, and the other one will be V. So it just simply takes all the parameters, it takes the learning rate, and it will automatically optimize. We'll see how to use this optimizer. Now just let's check our models properly. What is there? So when you call list.models, now how many model lists are there? So there are like total of 4, 1, 2, 3, 4. We will see what are these. So first model is of first weight is of size 100 cross 784. You see, this is like it takes 784 as the input and 100 is the number of hidden layers. So that's what it is, 784 cross 100, and 100 is the number of bias. So it is not just W time W x x transpose plus W. There is also a addition term to x transpose W plus B. So that's how linear model will look like, right? X transpose W plus a bias term B. In our previous lecture, we did not add a bias term, but in general, a bias term is simply a constant that you want to add to your network, okay, which is independent of the input. When you add plus B, it is independent of the X that you feed in, okay. So this is this. So layer 1 has, excuse me. So a layer 1 has 100 of bias because this is what the bias is from the hidden size. And the second layer, second V, has 10 cross 100, which takes 100 is the hidden layer, which is this V value, 100 is the hidden layer, and 10 is the output layer. So the V matrix size is 10 cross 100. And here too, again, there is a bias of 10. So there are 10 biases that have been added. So let's run this thing. So that's what we get. So this is your model, which is, as we predicted, this is the same. Now this is where we start learning. Okay, so now we will do this gradient descent algorithm. So now you have, so you have the model here. You have your sum weight here. You calculate the gradient and you want to move in the negative direction of the gradient. And you keep on moving until you reach the optimal value or until you exhaust your effort. Say for example, in our case, we will just run for 3000 iterations. You see there are 3000 iterations that we have set, which we have converted into number of epochs. So we'll run only for 3000 iterations, or number of epochs there. Okay, so this is the for loop that we will only run for this much maximum number. We start by taking some images and labels from the training data. We will start viewing all these images as a 784 cross images. We will set the gradient to 0. So you need to, this is very important step. You need to first make sure that your optimizer does not have any pending gradients. You calculate the model's output on the images. Required grad is not needed. You calculate all the outputs for the model images. You calculate the loss using the cross entropy loss. You remember the criteria that we have defined? Criteria is cross entropy loss. So you define your loss and you simply call loss.backward. This step will calculate the gradient of the parameters and it will store in the optimizer. Now the only thing that you have to do is call optimizer.step. When you call optimizer.step, it automatically does this part. So WT minus eta types in the negative direction of the gradient. So when you call this optimizer.step, it automatically does these parts. So now your optimizer will update your model's parameters. This model's parameters have automatically been updated by your optimizer now. You increase the iteration because you do want to make sure that you do not have more than 3,000 iterations or the number of epochs. So you increase your iteration, and for every 500, as soon as you reach every 500 iterations, you want to check the accuracy of your model. So you actually start loading your test data, so which is images and label. You convert them into images and label. This also does not require. And once you convert them, so you have images. Now you output, you pass the images through the model, you get the output, and you try to predict what is the prediction of the output. You just choose the maximum value, right? Say some have low probability. In our example before, we predict if an image of car is passed, we will predict bike because the bike has highest probability here. Though we know that this is incorrect, that's why we say that it is has a lower accuracy. So that's what we do. We choose the maximum value of the 10 outputs that we have seen. That's what we call predicted. Now we have this is the total size. And we say that if the predicted is equal to the labels, the label is the true label, the true classification. If predicted and label are same, we say this is correct value. And we add all the correct values. We go through all the data set that is there in the test data set, and we calculate the total correct values. So how many correct that it has predicted, and we just calculate the accuracy, correct by total times 100. So this is the accuracy. Okay, so let's run this model. So you see that at iteration 500, the loss is 0.655. The accuracy is 85.80. So it is really nice. Now the loss has started decreasing. It has become 0.499, and the accuracy have also increased. The loss is also decreasing at 4.1. The accuracy have increased to 90%. The loss slightly increased though because it's a stochastic gradient descent, because the curve is not as such a good curve does not exist. So sometimes you will end up increasing a loss, but eventually you will decrease. So you see that the loss eventually decreased to 0.19 and then slightly increased a bit, but the accuracy is almost always close to 91, or in the last case it became 91.9, which is close to 92%. So that's how you're able to, you're only training. Notice that you're only training on the training data set. So you calculated the loss, you calculate the gradient of the loss, and you updated your model's parameter. But you never did such thing for the test data set. Test data set is only used to calculate the accuracy of the model. You never calculated You never use your test data set for learning the model parameters, and the accuracy was on test data set. So there are other things that you can do. That there are you can do batch normalization and dropout, but this we will not cover because this is a fairly advanced topic. But we will just point it out to you that if you can do these things, this also helps in improving your accuracy, and you can take this accuracy close to 96% too. So if you play with around this, so yeah, overall this is what the basic neural network architecture looks like. This is what we have today. Now, if you have any doubt, we will take doubts here now. If you have any doubt, any question,
No, sir.
okay. So I thought that there will be more questions or something, but if there are no further questions, I think this is what our tutorial is of today. I would request students to actually play with this tutorial. So next week you have a Kaggle competition, if I'm not wrong. Yeah, were you aware of what is the schedule for next week? Hello, hello. Uh, so next week you have we will be hosting a Kaggle competition where you have to complete a given task, and based on all the algorithms you have learned, based on what you have understood on your own experience. So we will be hosting that competition on this Kaggle platform. Let me just go through this Kaggle platform once. So this is how the Kaggle competitions will look like. So we will host your competition here. You need to create an account on this kaggle.com. You can see that there are multiple competitions that are already running. So there is this. This is a very basic competition that here you need to detect a disaster. So there's very fundamental, very basic Kaggle notebook where you can see there are training set, test set, and you need to build a model such that you can classify them properly. So we will be hosting a competition on this platform, similar to what is here. So you can start with this Titanic machine learning competition and housing price prediction problem, and you can start before the competition. We will be starting this competition maybe on Tuesday or Monday sometime. So we will take we will discuss how will this information be shared. Roshan will share these information properly to you, but the Kaggle platform is the one we will be using for. So we request everyone to create a account in Kaggle webpage. So you will go there and you will see and start participating in some fundamental ones like the Titanic machine learning competition or housing price competition, and apply all the knowledge that you have learned, all the information that you have learned in this lectures, and see whether you are able to beat how well you are able to perform on these challenging tasks. So it's not just that they are it is basics, but there are also with prize competitions too. So if you can, based on the if you can win all these competitions, you will also be awarded with the first prize, winning a very significantly large sum of money. You can see that this is close to $1 million though. So there you go. So these are the we will be hosting competition on Kaggle, and we request students that you should be able to participate in at least the fundamental ones, and improve your competency level so that you can participate in high priced events too. So yeah, so this is what we have for today. If there are no further doubts, then I think we can end the lecture. So let me just, before we end the lecture, let me share the notebook. Okay, can someone confirm if they can see the notebook? Okay. Thank you for confirming. Uh, so this ends the lecture for the total lecture. And neural network is also a sufficiently advanced concept, and it has become increasingly popular because it can, as you can see, that the neural network, no linear model can actually be learn a such classification. That given an image, classify it whether it is 0, 1, 2, predict what this image is. No linear model or complex model can learn such thing. Neural network has this interesting property that it can learn a fairly complex classification task. So I hope that you will use these models in your own way and play with it. All the tutorials that we did is shared with you. So please go through those tutorials again, and we will be still be there for another week, or you can reach out to us through the coordinator if you have any doubt there. Since I think you may need to take play with this tutorial by yourself to have some doubt, maybe probably that's why you are not able to ask out now. But even after this class, if you have any doubt, please reach out to any one of us, and we will try to address your doubt even then too. And next week you will have a competition that will be hosted on Kaggle. So go to Kaggle, play with some of the competitions that are already there, the basic and fundamental ones, and then we'll see. And towards the end, you will be able to see how well you are able to compete there, how well you did with your uh, modeling part. Okay, so this is it from my side. So if there are no further doubts, we can end the lecture then. Thank you again. Uh, yeah, this is it. So we can end the lecture now. Thank you all.